This is Rupesh Kumar from Government Polytechnic Narayankhet. Today I want to share some information regarding the combinational logic circuits. Topic is 4-bit parallel adder. Already we learned about the different adder circuit, that is half adder using XOR and OR gate, half adder using only NAND gates, half adder using only NOR gates, and full adder using two half adders and one OR gate. Today we will learn about the 4-bit parallel adder circuit. On completion of this period, you would be able to understand implementation of 4-bit parallel adder using full adder circuit, working of 4-bit parallel adder using full adders. These are the topics today we will cover in this session. Implementation of 4-bit parallel adder using full adders, working of 4-bit parallel adder using full adders. Already we learned about the what is half adder and what is full adder. Half adder means a half adder is a logic circuit that adds two binary digits. What is full adder? Full adder is a logic circuit that adds three binary bits. For both full adder and half adder, there are two outputs known as sum and carry. Inputs are different for full adder and half adder. For full adder, three inputs are there, A, B, C in. For half adder, two inputs are there, A, B. Once again repeating, what is a half adder? Half adder is a logic circuit that adds two binary digits. It is a combinational logic circuit which is having two inputs and two outputs. Inputs for half adder is A and B. Outputs for half adder is sum and carry. Boolean expression for half adder is S equal to A XOR B, that equal to A B bar plus A bar B. Okay. Now, what is a full adder? A full adder is a logic circuit that adds three binary bits. It has three inputs and two outputs. Three inputs are A, B, C in. Two outputs are sum digit as well as the carry out. The Boolean expressions for the full adder is sum equal to A XOR B XOR C in. For carry out equal to A XOR B C in plus AB, or AB plus BC in plus AC in. These are the Boolean expressions corresponding to full adder and half adder. Main difference between full adder and half adder is inputs as well as the full adder is it can take the carry also in it, but half adder does not take the carry. Main difference between the full adder and half adder. The truth table of full adder is given here. Already we learned about this. Here carry is an AND gate and sum is an XOR gate. Next, truth table of full adder. Here we already learned that carry out is AND plus, or sum is XOR plus XNOR. Carry output is A XOR B C in plus AB. Sum is A XOR B XOR C in. Now 4-bit parallel adder using full adders. 4-bit adder. A parallel adder or binary adder is a logic circuit that can add two binary numbers. A binary adder is a logic circuit that can add two binary numbers. A binary adder is a logic circuit that can add two binary numbers. The binary operation performed by the 4-bit parallel adder can be explained with the below example. Binary operation performed by the 4-bit parallel adder can be explained with the help of the below example. Here example is, let the two binary numbers that are to be added are A1 and B1, that is A3, A2, A1, A0 and B3, B2, B1, B0. Here we are getting the sum is S3, S2, S1, S0. Carry is C3, C2, C1, C0. Ci plus 1 is Cs, Cr, Cq, Cp. Here a binary adder is a logic circuit that can add two binary numbers. The binary operation performed by 4-bit parallel adder can be explained with the help of the below example. Let the two binary numbers that are to be added are A3, A2, A1, A0, that is AI, B3, B2, B1, B0, that is BI. Sum is getting is SI is S3, S2, S1, S0. Carry input is C3, C2, C1, C0. Carry output is CS, CR, CQ, CP. It is the symbol of parallel binary adder. Input is AB as well as Cin. It is carry input, and output is Cout and sum. It is the parallel binary adder which resembles our full adder circuit, which resembles our block diagram of full adder circuit. Inputs are AB and carry in, outputs are carry out and sum. It is symbol of parallel binary adder. Please make a note of it, symbol of parallel binary adder. I wish to share some information regarding the parallel binary adder, that is a single full adder is capable of adding 3 bits, 3 1-bit numbers or 2 1-bit numbers and a input carry. To add binary numbers with more than 1 bit, additional full adders must be employed. Okay, for that purpose we are using this parallel binary adder. Here consider the binary addition for two 4-bit numbers as given in this. Here inputs are A3, A2, A1, A0, as well as for B input B3, B2, B1, B0. Carries input is C3, C2, C1, C0. Here by doing the sum and carry operation, here we get the value that if any extra carry is developed, it should be given to the another number or given to the another full adder. For taking out that problem, we designed this 4-bit parallel adder. When one binary adder is binary number is added to another, each column generates a sum and a 1 or 0 carry to the next higher order sum column. To implement the addition of binary numbers with a logic circuit, a full adder is required for each column. Here we want to employ a full adder for each column. Hence, for 4-bit numbers, 4 adders are needed. Connected for 4 8-bit numbers, 8 adders are needed, and so on. Note that carry output of each adder is connected to the carry input of next higher order adder. Thus, several full adders are connected to form adders that add several binary digits at one time. This constitutes the first of all 4-bit adder, second one 8-bit parallel adder, third one 16-bit parallel adder, and so on. For doing 4-bit addition, we want to have 4 full adders we have. For 8-bit, 8 parallel full adders are there. Now 4-bit parallel adder. Here AI equal to A3, A2, A1, A3, A2, A1, A0 is known as AND. Here A3, A2, A1, A0 is known as AND. BI equal to B3, B2, B1, B0, it is known as added. A3, A2, A1, A0 is known as AND. B3, B2, B1, B0 is known as added. SI equal to S3, S2, S1, S0 is known as sum. And CI equal to C0, C1, C2, C3 is known as input carry. Ci plus 1 equal to Cp, Cq, Cr, Cs is known as output carry. Here I am giving the clear cut idea of the inputs and outputs in the above parallel adder example. AI equal to A3, A2, A1, A0 is known as AND. BI equal to B3, B2, B1, B0 is known as added. SI equal to S3, S2, S1, S0 is known as sum. CI equal to C0, C1, C2, C3 is known as input carry. CI plus 1 equal to CP, CQ, CR, CS is known as output carry. Please make a note of this 4-bit parallel adder in your notebooks. Most important one with example also. Here AND is there, addend is there, sum is there, carry out is there, carry in is there. We must know each and every part of the parallel adder for getting the outputs. Please note each and everything clearly and without any mistake. A binary adder is a logic circuit that can add two binary numbers. The binary operation performed by the 4-bit parallel adder can be explained with the help of below example. Let the two binary numbers that are to be added are C3, C2, C1, C0, that is CI, A3, A2, A1, A0, that is AI, B3, B2, B1, B0, that is BI, S3, S2, S1, S0, that is SI, CS, CR, CP, CQ, that is CI plus 1. Okay, all of you written in your notebooks 4-bit parallel adder. Next one, please write this one also. AI means, BI means, SI means, CI means, and CI plus 1 means. AI means A3, A2, A1, A0 is known as AND. B3, BI means B3, B2, B1, B0 is known as added. SI means S3, S2, S1, S0 is known as sum. CI means C0, C1, C2, C3 is known as input carry. CI plus 1 equal to CP, CQ, CR, CS is known as output carry. Okay, completed. Going to next one. Here addition of LSBs. Here inputs are AB, carry is Cin equal to 0 and carry out sum. Here I have given a full adder circuit equivalent to the half adder. That means if Cin value is equal to 0, the total circuit represents the half adder. A full adder with one grounded input acts as an half adder. A full adder with one grounded input acts as an half adder. Okay, please make a note of it. Addition of LSBs. Addition of LSBs here. How to change the full adder to half adder? It is the session. It is not given in any textbooks, any internet also. Please note down this one, most important one. How to change full adder to half adder. A full adder with one grounded input acts as an half adder. A full adder with one grounded input acts as an half adder. A full adder with one grounded input acts as an half adder. Okay, completed. Next one. It is the 4-bit parallel adder using full adders. See here, 4 bits are, we must generate 4 sums and 4 Couts and 4 carries and 4 inputs AND and addends also. For that we are using 4 full adders, FA0, FA1, FA2 and FA3. Here see, first of all C input is equal to 0 and first Cout is connected to the second Cin, second Cout is connected to third Cin, third Cout is connected to fourth Cin. Okay, see, I have clearly mentioned the inputs and outputs corresponding to it. A0, B0 is the input values for FA0. A1, B1 is the input values for FA1. A2, B2 is the input values of FA2. A3, B3 is the input values for FA3. Next, output values of sum is S0 for FA0, FA1 S1, FA2 S3, FA2 S2, FA3 S3. Okay, please draw this 4-bit parallel adder using full adders in your notebook. 4-bit parallel adder using full adders. Four-bit parallel adder using full adders. Okay, completed. Next diagram, construction details. For adding LSBs, either half adder or full adder is used. The carry output of each full adder is connected to the carry input of next higher full adders. I have already told to you, for adding the least significant bits, either half adder or full adder is used. You already know LSB means least significant bit, MSB means most significant bit. The carry output of each full adder is connected to the carry input of next higher full adders. Now working of 4-bit parallel adder using full adders. The working can be explained with two binary numbers that are to be added. Here input A equal to 1011, B equal to 0011. We are doing the input carry is 0110. For full adder, 0 inputs are A0 equal to 1, B0 equal to 1 and C0 equal to 0. See here, from LSB to MSB we are going. So please view the LSB bits 1, 1, 0. A0 equal to 1, B0 equal to 1 and C0 equal to 0. It produces sum. It is equal to 0 and carry equal to 1. It produces the sum equal to 0 and carry equal to 1. C1 equal to 1. Okay. See here, carry equal to 0. Inputs are A1, B1. I have given in that carry output is sum is equal to 0 and carry input equal to 1. Sum is equal to 0 and carry input equal to 1. Then we are taking the another A1, B1 value, that is 1, 1. Now 1 plus 1 plus 1 is sum equal to 1 and carry equal to 1. Here see, sum is equal to 1 and carry equal to 1. Now we are taking the another values A2 equal to 0 and B2 equal to 0. By adding these three, 1 plus 0 plus 0, it is equal to 1. Sum is equal to 1 and carry equal to 0. Sum is equal to 1 and carry equal to 0. Now taking another values A3 1, B3 0. 0 plus 1 plus 1, we get the value that sum equal to 1 and carry equal to 0. That carry is equal to sum. So 0, 1, 1, 0 is the answer. See here, for full adder 1, inputs are A1 equal to 1 and B1 equal to 1. And the carry from the full adder 0 is C1 equal to 1. It produces sum S1 equal to 1 and carry C2 equal to 1. Now for third full adder, inputs are A2 equal to 0 and B2 equal to 0 and C2 equal to 1. It produces sum S equal to 1, S2 equal to 1 and S3 equal to C3 equal to 0. For the fourth full adder, 3 inputs are A3 equal to 1, B3 equal to 0 and C3 equal to 0. It produces the S3 equal to 1 and C4 equal to 0. Augend is 1011 AI, addend is 0011 BI, If input carry equal 0 1 1 0, that is Ci, output S3 or Si equal to 1 1 1 0, C out equal to 0. So here values are 1 0 1 1 plus 0 0 1 1 equal to 0 1 1 1 0. Number of full adders to add to n-bit numbers is by using more full adders. We can build binary adders of any length. For doing many bit full adder operation or addition operation, we can build many binary adders of any length. An n-bit adder requires n full adders with each output carry connected to the input carry of the next higher order full adder. An n-bit adder requires n full adders with each output carry connected to the input carry of the next higher order full adder. For example, to add 16-bit numbers, we need 16 full adders. For example, to add 8-bit numbers, we need 8 full adders. Summary. We have discussed the implementation of 4-bit parallel adder using full adders, working of 4-bit parallel adder using full adders. These are the two topics which we discussed today. Implementation of 4-bit parallel adder using full adders, working of 4-bit parallel adder using full adders. Now going for the quiz. A logic circuit that can add two numbers. A binary adder, B subtractor, C inverter, D none. Answer is a binary adder, that it is also known as a half adder. A logic circuit that can add two numbers is a binary adder. Next one, second one, a logic circuit that accepts 2 bits as input and produce their sum and carry outputs. That is answer A full adder, B half adder, C multiplier, D all the above. A logic circuit that accepts 2 bits as input and produce their sum and carry outputs is a half adder. Answer is A half adder. Next, third one. A logic circuit that accepts two 1-bit signals and carries in as inputs and produce their sum and carry as outputs is A half adder, B full adder, and C both A and B, D none. Answer is B full adder. Next, fourth one. A adder for adding multi-bit numbers and accepting all the bits simultaneously is A serial adder, B parallel adder, C both A and B, D none. Answer is A parallel adder. B parallel adder. An adder circuit for adding multi-bit numbers and accepting all the bits simultaneously is B parallel adder. I have given the frequently asked questions here as well as the assignment questions. Please note down these questions and complete the assignment before the next session. Implement 4-bit parallel adder using full adders. Explain the working of 4-bit parallel adder by using full adders with a neat sketch. Explain the working of 4-bit parallel adder by using full adders with a neat sketch. Okay, it is the full adder using 4-bit parallel adder. Most important question is how many bits we want to add. We must have how many? We must have that number of full adders. 4-bit means 4 full adders. 6 bits means 6 full adders. 8-bit means 8 full adders. 16-bit means 16-bit full adders. Okay. Now I will give once again the four-bit parallel adder using full adders operation. Working conditions of the 4-bit full adders and 4-bit parallel adder using full adders. A 4-bit parallel adder is shown in figure. Okay, the numbers being added are written as A3, A2, A1, A0 and B3, B2, B1, B0. Numbers from the least significant bits of the two 4-bit adders. Numbers are represented by A0, B0. For first full adder, it should be pointed out that either a half adder can also be used to least significant position on the carry input of the full adder is made 0, because there is no carry in the least significant position, that is equal to carry input is equal to 0. After the addition in the first full adder, whatever the carry takes place, that is transferred to the second full adder. Thus the carry output of each adder is connected to the carry input of the next higher order adder. The next higher order bits are A1 and B1 are presented on the second full adder, and so on. Addition operation is repeated in all the full adders, resulting the sum bits S0, S1, S2, S3 and S4. Notice that output of carry from the leftmost full adder becomes the most significant sum bit, that is equal to S4. For example, when we want to add 2-bit numbers, that is, here already we have a explanation. 2-bit number is 1011 and for B it is 1101. 0011. The least significant bits of two numbers is 11, which are entered into the first adder here. See, 11 is given in the first full adder. The sum is equal to 0 and carry output, that is Cout 1, is given to the second full adder as the third input. In addition to this input, the second column bits of two numbers are 1 and 0. That is 1, 1 are entered into the second full adder as inputs. Then the sum is equal to 1 and carry is equal to 1 is transferred to the third full adder. This carry 1 and sum values is equal to 1 is transferred to the next full adder, and most significant numbers bits of two numbers are 0, 1 are entered into the fourth full adder. Then it results the sum outputs S3 as equal to 1 and becomes the most significant bit S4. The resultant sum is 0, 1, 1, 1, 0. The resultant sum is 0, 1, 1, 0. It is the working of the full adder circuit. Once again I am repeating this one. Working of 4-bit parallel adder using full adders. 1 minute. Okay, it is clearly understandable. Next one, construction details. Here I have shown the 4-bit parallel adder here. For adding least significant bits, either half adder or full adder is used. The carry output of each full adder is connected to the carry input of next higher full adders. The carry output of each full adder is connected to the carry input of next higher full adders. Now working of 4-bit parallel adder using full adders. See here, the working can be explained with two binary numbers that are to be added are input carry, that is first one A again it equal to 1011, next add and B equal to 0011, and carry inputs are, first of all LSB input is equal to 0. Now we are going to add 1 plus 1 plus 0 equal to sum is equal to 0 and carry is equal to 1. Okay, it is given to the carry input of next full adder, that is 1. Now we are adding these 3 bits, 1 plus 1 plus 1. We are getting the value that sum equal to 1 and carry equal to 1. Carry is given to the next higher order bit, that is 1 plus 0 plus 0. We are getting the value 1. Is sum and 0 in carry. 0 plus 1 plus 0, we get the value that sum is equal to 1 and carry equal to 0. Now the output is 0, 1, 1, 1, 0. For the full adder, 0 inputs are A0 equal to 1, B0 equal to 1 and C0 equal to 0. It produces S0, that is sum equal to 0 and carry C1 equal to 1. Sum equal to 0 and carry C1 equal to 1. See here, clearly here I have shown the input values as well as output values, that is AND and addend as well as the carry in. See, in first one, C input equal to 0 and A0 equal to 1 and B0 equal to 1. We get the sum value is equal to 0. Once again, you can also take the addition here, 0 plus 1 plus 1. We already know that binary addition, 0 plus 0 equal to 0, 0 plus 1 equal to 1, 1 plus 0 equal to 1, 1 plus 0 equal to 1 0, 1 plus 1 plus 1 equal to 1 1. Here 1 plus 1 is sum 0 and carry 1. Green color represents the 1 and green color represents the carry, red color represents the sum. Now we are taking another 2 input values, that is A1 equal to 1, B1 equal to 1. Here input C input is 1. Now we add 3 bits, 1 plus 1 plus 1. We get the value that sum equal to 1 and carry equal to 1. Then next we are taking another inputs, that is A2 equal to 0 and B2 equal to 0 and Cn equal to 1. Now we add these 3 bits, 0 plus 0 plus 1. We get the value that sum equal to 1 and carry equal to 0. And next 2 bits are, that is the final full adder bits are A3 equal to 1 and B3 equal to 0. Now add 3 bits, 0 plus 1 plus 0. We get the value that S3 equal to 1 and carry out is equal to 0, that is nothing but S4. Now the total value is 0, 1, 1, 1, 0. Here I have explained it in sentence format also. Please have a look of it. For full adder 1, inputs are A1, B1, A1 equal to 1 and B1 equal to 1. And carry on the full adder 0 is C1 equal to 1. It produces sum S1 equal to 1 and carry C2 equal to 1. For the full adder, third full adder 2, inputs are A2 equal to 0 and B2 equal to 0 and C2 equal to 1. It produces S2 sum equal to 1 and carry C3 equal to 0. Similarly, for the fourth full adder, 3 inputs are A3 equal to 1, B3 equal to 0, C3 equal to 0. It produces sum S3 equal to 1 and carry C4 equal to 0. That equal to S4 equal to 1. Now here I have given the AND values, that is 1011 equal to AI, added values 0011 that is equal to BI, input carries are 0110 and sum values are 1110 and carry out value is equal to 0. Now we get the value that 1011 equal to 1011 plus 0011 equal to 01110. Number of full adders to add 2 n-bit numbers is by using more full adders. We can build binary adders of any length. An n-bit adder requires n full adders with each output carry connected to the input carry. Output carry is connected to the input carry of next higher order full adder. Next, for example, to add 16-bit numbers, we need a 16 full adders. For example, to add 16-bit numbers we need 16 full adders. Now I wish you share some more information regarding the 4-bit full adder. That is, a single full adder is capable of adding 3 1-bit numbers or 2 1-bit numbers and an input carry. To add binary numbers with more than 1 bit, additional full adders must be employed. Consider the binary addition for 2 4-bit binary numbers. When one binary number is added to another, each column generates a sum and carry. The carry is to be sent to the next higher order column. To implement the addition of binary numbers with logic circuits, a full adder is required for each column. Hence, for 4-bit numbers, 4 full adders are needed. And for 8-bit numbers, 8 full adders are needed. For 16-bit numbers, 16 full adders are needed, and so on. Note that the carry output of each adder is connected to the carry input of next higher order adder. Thus, several full adders are connected to form adders that add several binary digits at one time. Thus, several full adders are connected to form adders that add several binary digits at one time. Now, going to the section that 4-bit parallel binary adder. It is shown in the before slides. The number being added are written as A3, A2, A1, A0, that equal to AND B3, B2, B1, B0, that equal to added. Carry in is C3, C2, C1, C0. Carry out is CR, CS, CQ, CP. Now, numbers from the least significant bits of the 2-bit numbers are represented by A0, B0. Next one is A1, B1. Next one is A2, B2. Next one is A3, B3. These are, first of all, A0, B0 are entered into the first full adder. It should be pointed out that either a half adder can also be used for the least significant bit position or carry input of the full adder, or carry input of the full adder is made equal to 0 because there is no carry into the least significant position at first. After the addition in the first full adder, whenever or whatever the carry takes place, that is transferred to the second full adder. Thus, the carry output of each adder is connected to the carry input of the next higher order adder. Next higher order bits are A1 and B1 are presented to the next second full adder, and so on. Addition operation is repeated in all full adders, resulting the sum bits S0, S1, S2, S3 and S4. Notice that the output carry from the leftmost full adder becomes the most significant sum bit, that is equal to S4. Now I will give one more example for you. Please write down in your notebook, that is AND AI equal to 1011, AND BI equal to 1101. Please do this operation in your notebook and inform me what is the output and what is the output, that is carry out, sum as well as CI. I will also tell you simple tricks. That is, for example, when we want to add two 4-bit numbers 1011 and 1101, the least significant bits of the two numbers are 11 here are entered into the first full adder. First of all, you enter 11 in the first full adder, that is A0, B0. The sum output is 1 plus 1 is equal to 0 sum and carry 1. Sum output S0 is equal to 0 and carry output C0 equal to 1. carry output C1 equal to 1 is transferred to the second full adder as the third input. In addition to this input, second column bits of the two numbers are 1, 0 are entered into the second full adder as inputs. Then the sum outputs S1 equal to 0 and carry output is equal to 1 is transferred to the third full adder. This carry 1, 0 and 1 third column inputs will be connected to the third full adder. Thus the sum output S2 is equal to 0 and carry is equal to 1 is transferred to the fourth full adder. This carry 1 and the most significant bits of the two numbers 1 and 1 inputs are entered into the fourth full adder. The resulting the sum is S3 equal to 1 and S4 equal to, or that is carry output is equal to 1 becomes the most significant bit S4. The resultant sum is, what is the resultant sum? 1 1 0 0 0. That means here AND is 1 0 1 1, AND is 1 1 0 1. Sum is 1 0 0 0, carry out is 1. Total constitutes the 1 1 0 0 0. Total constitutes the 1 1 0 0 0. Please make a note of it and please complete that one. Once again I will show you the quiz one also. 1 minute. Here the logic circuit that can add two numbers is binary adder. It is also known as full adder, half adder also. Okay, binary adder is half adder also. Next, two logic circuit that can accept 2 bits as input and produce their sum and carry outputs is a half adder. It is half adder. That means half adder has 2 inputs and 2 outputs. Inputs A and B, outputs sum and carry. 3. A logic circuit that accepts 2 1-bit signals and carry in as inputs and produce their sum and carry as outputs is B, full adder. Full adder has 3 input values, that is A, B and C in outputs as sum and carry. Now fourth one, a adder circuit for adding multi-bit numbers and accepting all the bits simultaneously. That means that is the answer is B, parallel adder. An adder circuit for adding multi-bit numbers, that is 4-bit or 5-bit or 6-bit, 10-bit, any bits, and accepts all the bits simultaneously is parallel adder only. Okay. Once again I am told that for 4 input 4-bit addition we want to have 4 parallel adders. For 8-bit addition we want to have 8 full adders. For 16-bit addition 16 full adders required. And one important thing also is there, that is the carry input of LSB bit is given to the carry output of first full adder is given to the carry input of next higher order full adder. Most important one, please note in your notebooks. Carry output of first full adder is given to the carry input of next higher order full adder. Okay, this is the 4-bit parallel adder. I think I reach your expectations in 4-bit parallel adder explanation. Thank you for your patience for hearing my class. Thank you so much.